When some of the most renowned firms in architecture, engineering, and construction collaborate on a single project, the result is more than just a building. It is a feat of precision and innovation. At Toranomon Hill Station Tower, five industry leaders, Neyen Partners, Kajima Corporation, Taisei Corporation, OMA, and ARUP brought together their expertise to address one of Tokyo's most complex urban developments. The challenge was clear: construct a new subway station beneath an active metro line, integrate a high-rise tower above, and establish a seamless pedestrian network, all within one of the city's most densely built environments. Achieving this required advanced underpinning techniques to stabilize existing structures, shotcrete reinforcement to strengthen tunnels, and large-scale pedestrian infrastructure engineering to ensure uninterrupted urban mobility. This ambitious vision was realized in the form of Toranomon Hill Station Tower, a development where infrastructure, urban design, and engineering merge into one integrated system. Strategically positioned in Minato City, Tokyo, Toranomon Hill Station Tower serves as a key transit hub, seamlessly linking to the Tokyo Metro Hibiya Line. The development comprises the station tower, underground and above ground levels, and the T-deck, each serving distinct functions. The underground level is seamlessly integrated with Toranomon Hill Station, ensuring efficient pedestrian movement between the station and surrounding facilities. The first floor houses the station concourse, while the basement level connects directly to the subway platform and ticket gates. Adjacent to this, a plaza and ticket gate area provide an open and accessible transit place. Additionally, station atrium, designed as an all-weather environment, features an open structure flooded with natural light. To fully understand the complexity of this development, it is essential to examine the construction of Toranomon Hill Station, a critical component of the project that seamlessly integrates with the station tower above. Toranomon Hill Station is a new station on the Tokyo Metro Hibiya Line, built 56 years after the line first opened. It is located between Kasumigaseki Station and Kamiyacho Station, with construction led by Kajima Corporation covering civil engineering, architecture, and electrical work. One of the biggest challenges was removing part of the existing Hibiya Line tunnel to create the new platform. The site was in a highly dense urban area with heavy traffic on National Route 1 and Ring Route 2, as well as numerous underground utility pipes surrounding the tunnel. The project started in February 2016 since the subway was operating normally. The underpinning method was used to support the tunnel during excavation. The construction team also implemented reinforcement and safety measures to avoid disruptions to train operations. Most of the work was done between 1 a.m. and 4 a.m. when trains were not running. To minimize damage to the existing structure, two key methods were used: shotcrete method and underpinning method. Shotcrete method is high-pressure concrete spraying to reinforce tunnels and aging structures. Underpinning method is strengthening the foundations of existing structures. Thanks to these advanced techniques, the project was successfully completed in 4.5 years. With the completion of Toranomon Hill Station, the focus shifted to constructing the station tower above, a project that came with its own set of engineering challenges. One unique feature of Toranomon Hill Station Tower is that its second basement level serves as a road, with the Ring Route 2 underground tunnel passing through this level. This required innovative construction methods to ensure stability and efficiency. Given the constraints of an active subway line below and a major road running the side, the construction team adopted specialized techniques to ensure structural stability, seismic resilience, and efficient use of space. First method is foundation piling method. Large diameter piles, which is 1.5 meters wide, were drilled and filled with reinforced concrete to ensure stability. Second, knuckle wall piles method. This technique used in the construction of Dokyo Skytree enhances earthquake resistance by increasing ground stability. Third, top-down construction method. Unlike traditional methods, the first floor was constructed first, while excavation for the basement levels continued below. Fourth, reverse truss method. Steel beams were inserted into foundation piles to firmly support the first floor. Finally, CFT, concrete filled tube method. Concrete was injected into steel columns extending up to the 47th floor at a height of 207 meters, ensuring high strength and seismic resistance. These innovative techniques enabled the tower to be constructed safely and efficiently within one of Tokyo's most complex urban environments. At the heart of Toranomon Hills, the T-deck serves as a vital pedestrian corridor connecting Mori Tower and Station Tower, spanning Sakuradadori Avenue. With a 20-meter width and 60-meter length, it strengthens the urban network while ensuring smooth pedestrian flow. This structure was entirely designed using grasshopper and constructed with the off-site construction method. The OSC method, the off-site construction method, is an efficient approach where building elements are designed, manufactured, and assembled off-site before being transported for final installation. This method significantly enhanced precision, reduced on-site disruptions, and streamlined the construction process. The continuous girder system applied in the deck structure evenly distributes loads across multiple points, minimizing stress concentrations and reducing deflection. This system not only enhances structural stability, but also allows for a lighter yet stronger framework, optimizing material efficiency and reducing long-term maintenance needs. Additionally, origami-inspired geometric design principles were integrated into the structural framework, improving load distribution and overall rigidity while maintaining material efficiency. Above the deck, the polyhedral canopy provides protection from wind and rain while blending seamlessly into the urban landscape. Its multifaceted surface enhances aerodynamic performance, allowing it to withstand strong winds while maintaining structural integrity. Constructed with high-precision CNC machined steel components, the deck maintains millimeter-level accuracy for structural integrity. A hybrid connection system combining bolted joints for easy maintenance and welded sections for strength further enhances its seismic resilience. More than just a bridge, the T-deck is a key piece of urban infrastructure and enhancing pedestrian safety and connectivity within Toranomon Hills. Next, we'll discuss the building's spatial configuration, structural characteristics, and the analysis conducted to ensure its stability. The floor plan is divided into 3 functional zones. First, the eastern section consists of an office band. Second, the central area features an activity band designed to accommodate dynamic urban functions. Third, the lower levels integrate with the underground spaces, enhancing spatial continuity and providing a more open environment. From a structural perspective, the office periphery is reinforced with enclosed walls, ensuring stability, whereas the southern facade remains open to mitigate wind effects. The main building utilizes a steel frame structure with trusses applied to the lower levels to create expansive open spaces in response to the tower's distinctive architectural form. A large span MEP box is strategically positioned beneath the western trusses, optimizing space for mechanical, electrical, and plumbing systems. Additionally, concrete-filled steel columns are incorporated at the base to enhance structural integrity. At the eastern entrance, branched steel columns are introduced to facilitate efficient load transfer from the upper structures. Finite element method FEM modeling was employed to analyze this section, ensuring that loads are effectively distributed. The FEM model included floor slabs to simulate real-world conditions with loads ranging from 2 to 5 tons and upper columns modeled up to 3 meters in height. The load analysis considered wind loads and seismic forces with a particular focus on L2 level seismic loads to evaluate their impact on the upper structure. Stress distribution analysis was conducted to verify structural safety, confirming that all components meet the required stability criteria. Tournament Hill Station Tower is a benchmark in integrated urban development, where infrastructure, architecture, and engineering converge seamlessly. The project's precision-driven execution, from subterranean station construction to high-rise structural innovation, demonstrates cutting-edge solutions for complex urban challenges. With advanced engineering, efficient spatial planning, and a commitment to connectivity, the development not only enhances Tokyo's urban mobility, but also sets a new standard for future cityscapes. It is more than a structure, it is a dynamic urban node redefining the built environment.